Hello everyone, my name is Anthony Cabrera, and I am a software engineer in the Architectures and Performance group at Oak Ridge National Laboratory. In this video, I will present a collaborative effort between Oak Ridge, the University of Oregon, and Washington University in St. Louis that showcases our efforts toward evaluating high-level synthesis portability and performance between Intel and Xilinx FPGAs. As the promise of performance gains due to Moore's law slows, FPGAs are emerging as a form of accelerator that enables the development of hardware solutions specific to a given application or domain. Additionally, FPGAs allow for such custom hardware designs without having to go through the cumbersome and expensive process of designing application-specific integrated circuits. The increase in interest of FPGAs is notably evidenced in industry, with completed and planned acquisitions of major FPGA vendors, as well as the increased availability of FPGA-attached compute instances in the cloud. The traditional workflow for generating FPGA hardware is shown in this diagram. A user defines their design in a low-level language such as Verilog or VHDL, and then runs their design through a toolchain specific to the target FPGA. At the end of this process, a bit stream is generated that is used to configure the target FPGA. However, FPGAs are notoriously difficult to program because users must reason about their designs at the level of logic gates, and this requires in-depth knowledge of digital design. This level of understanding is usually out of reach for typical software developers. However, high-level synthesis, or HLS, aims to circumvent this problem. Instead of using a low-level language, HLS allows users to specify their designs using a higher-level language such as C or C++. The difference between an HLS workflow and the traditional one is shown in this modified diagram. The vendor-provided toolchain is augmented with a front end that translates the high-level design into an RTL specification that then gets fed into the original FPGA toolchain. We refer to this augmented toolchain collectively as the hardware compiler. The hardware compiler abstracts away a large part of the difficulty of programming FPGAs. Intel and Xilinx, two of the major FPGA vendors, both supply HLS toolchains. In fact, there are many examples in the literature where HLS designs perform at least as good, if not better, than their low-level design counterparts. Moreover, Intel and Xilinx FPGAs can both be targeted using OpenCLC. Thus, in theory, designs for one FPGA should be portable for the other and vice versa. The implications of this are immense, as developers could easily move designs from one FPGA to the other. However, the question of portability and performance in this context is not as well examined. Thus, in this work, we begin to explore the question, how portable and performant are HLS designs between Intel and Xilinx FPGAs? To this end, our contributions are as follows. We detail our approach of porting FPGA designs originally architected using OpenCLC for an Intel platform to OpenCLC for a Xilinx one. Then, we evaluate the performance that results from the porting effort. Additionally, we present our experience using Xilinx Vitis, the environment which succeeds Xilinx SDXL in the HLS design process, as well as contribute to the sparse existing literature of OpenCLC designs that target Xilinx FPGAs. In this presentation, however, we will focus on the former 2 points. Our porting effort can be described in 3 parts. The first part is describing the kernels that we selected for our porting effort. We start with well-studied applications from the literature. Specifically, we select a subset of Intel OpenCL FPGA implementations, created by Zahouri et al., of the Rodinia benchmark suite. The applications we selected are shown in the table on the right. The original benchmark suite, created by Che et al., was intended to help benchmark a wide range of parallel computing patterns on emerging architectures of that time, which included GPUs and multi-core CPUs. Zahouri et al. Extended Rodinia to include Intel FPGA OpenCL implementations. In their work, they took a structured approach to kernel design by implementing baseline, basic, and advanced versions of each kernel, where each version used one or more combinations of FPGA optimizations recommended by the Intel Best Practices Guide. In this work, we port 2 kernel versions of each application in our subset, the baseline version and the best version, where the best version is the most performant version reported by Zahouri et al. The next part of our porting effort involves our modifications to the host side code originally intended for the Intel OpenCL FPGA implementations. In general, the host side code is responsible for managing the OpenCL constructs required for the OpenCL host and its associated devices. For example, this includes creating a device context, setting up host and device buffers, and enqueuing kernel invocations. A convenient feature of using OpenCL in our evaluation is that the structure of the host's code largely can remain the same even though we are evaluating a Xilinx FPGA. A salient change that we do make, though, is to leverage C++-like objects and to utilize the concept of resource acquisition as initialization, since most of the code is written using C-style constructs, but is compiled using a C++ compiler. Often, it is hard to keep track of the functionality of the different variables and routines that exist in the code, and explicitly managing memory is often error-prone. Thus, we create classes that are responsible for managing the OpenCL environment in each application, as well as classes that manage the variables and routines specific to each benchmark. This makes debugging and understanding the host-side code much easier. Finally, the last and most involved part of our porting effort is to port the OpenCL-C FPGA optimizations intended for an Intel FPGA to OpenCL-C designs targeting a Xilinx FPGA. Before moving on, it is worth noting that in the Xilinx HLS design process, it is possible to use C or C++ directly during kernel design instead of OpenCL-C. While this is true, I'd like to reiterate that in this work we are more interested in the performance portability between OpenCL-C kernel specifications in order to evaluate potential reuse between platforms. Idiomatically, why reinvent the wheel? If it is possible to get good performance from the same kernel specification, why not take advantage of it? To be sure, though, we plan to investigate the porting of Intel OpenCL-C kernels to Xilinx C or C++ ones in future work. We first start with porting the baseline versions for each kernel. Each baseline kernel is originally implemented using the single work item execution model. In this model, the work to be executed is wrapped in a loop that is managed by a single thread. This is in contrast to the multiple work item execution model, in which the work is not constrained to a loop and is divided among multiple threads. The single work item model, in many cases though, is best suited for the resulting FPGA design as a compute pipeline that accounts for non-trivial dependencies between iterations and that is specific to the kernel specification can be constructed. In the baseline versions of each kernel, there are no FPGA-specific optimizations within the kernel specification. This is helpful in two ways. First, it makes porting the baseline kernels to the Xilinx platform trivial since no optimizations need to be ported. Second, the resulting FPGA hardware synthesized from these kernels serves as the baseline to the FPGA designs that will result from porting the most performant versions of each kernel. Porting the versions of the kernels that yield the best performance in comparison is non-trivial. Before we discuss what needs to be done in order to successfully port FPGA optimizations, we want to explicitly express a goal that we have during the porting process. If a Xilinx counterpart to a given Intel optimization exists, we want to perform the minimum amount of effort necessary to port that optimization to its Xilinx counterpart. This means that we want to modify the kernel as little as possible while still expressing whatever the performant construct is in the resulting Xilinx design. Loosely, we claim that optimizations that are more difficult to port are less portable. In the following slides, we will detail two different optimizations, one of which is a straightforward one, and one of which is more difficult. Loop unrolling is a strategy employed in HLS that allows the compiler to utilize more of the FPGA's resources in order to spatially replicate the loop body a user-specified or compiler-determined number of times. By doing this, multiple iterations can execute concurrently, which can increase compute throughput. Though the specifications are different, this optimization exists for both the Intel and Xilinx platforms, and the mapping between the two is straightforward. For the Intel implementation on the left, the user supplies a hint to the hardware compiler via a pragma that directs the hardware compiler to replicate the loop body, in this case, 8 times. Similarly, this is accomplished on the Xilinx side on the right through the use of attributes. This optimization would be classified as highly portable because the Intel to Xilinx mapping for this optimization has a 1-to-1 relationship. A shift register is a cascade of individual registers, where the output of one register is tied to the next one. Shift registers are another useful FPGA construct to implement because of their many uses. One such use is as a sliding window. Some applications, such as the Pathfinder application in this work, use sliding windows as a way to buffer data in order to eliminate unnecessary trips to and from global memory. Unlike the previous optimization, the mapping between Intel and Xilinx in this case is non-trivial. In this example, we have a minimum working example of shift registers for both platforms. On the Intel side on the left, a local buffer of a size known at compile time is declared. This will serve as our shift register and will be mapped to local on-chip resources. In the first loop nest, the last element of the shift register is set to the currently indexed element of the global buffer input R. In the second loop nest, the I+1 element of the shift register is being shifted to the ith element. In order to concurrently execute these shifts in true shift register fashion, the loop must be fully unrolled. With this hint, this pattern of computation can be recognized by the hardware compiler and will be inferred as a shift register in the final FPGA design. On the Xilinx side, we must also declare a local buffer, but we must augment it with an attribute that completely partitions the array. This signals to the hardware compiler that the user wants the buffer to be constructed of individual registers. Then, the innermost loop must be unrolled, just like on the Intel side. While seemingly similar, this optimization becomes less portable depending on the parameters of a given application. Specifically, the size of the shift register to be inferred plays a big role in the performance and if it's even possible to infer a shift register. In this section, we evaluate the results of performing the ports of the Intel OpenCL FPGA kernels to Xilinx ones as detailed in the previous section. The FPGA card used in this work is the Xilinx Alveo U250 Data Center Accelerator card. We will first discuss the results of the minimum effort ports. This figure shows the performance of the minimal effort ports of the most performant Intel kernel versions ported to a Xilinx FPGA. In the results for the SRAD application, we observed that the minimum effort port of the most performant Intel kernel achieves a 36% speedup over its baseline counterpart. The FPGA kernel in this application takes advantage of shift registers as sliding windows as discussed previously in order to buffer data and save trips to global memory for both a reduction operation and a stencil operation. While this application demonstrates that it is possible to achieve a performance increase with a minimum effort port, our other applications show that minimum effort ports may not affect performance, or worse, might even drastically degrade performance. This is counterintuitive, since providing hints to the compiler to improve performance actually results in the opposite effect. To this end, looking at the Pathfinder results shows that the minimal effort port of what should be a more optimal version is actually 50 times slower than its baseline counterpart with no optimizations. The size of the shift register in the original Intel implementation was over 32,000 elements wide. In keeping with our goal of a minimum effort port, we apply that same parameter to the Xilinx kernel. However, the Xilinx hardware compiler will not allow for an array to be partitioned more than 1024 times. Thus, with this parameter value, we are unable to infer a shift register. Even worse still, a closer look at the hardware compiler logs for this kernel shows that the main loop of the computation was not able to be pipelined. This means that one iteration of the kernel cannot be launched until the previous iteration has finished, which degrades performance significantly. Ideally, an iteration of the kernel loop can be launched every cycle, such that an iteration of the loop can be executed every cycle. From this application, as well as CFD and Hotspot, it is clear that more effort is required in order to produce performant designs. Using Pathfinder as a representative application, we try to extract more performance from the most performant design by exploring different optimizations. In the coming section, we will focus on exploring the effects of partitioning the array cyclically, as well as sizing the shift register and the kernel such that one can be inferred by the Xilinx hardware compiler. This figure shows the results of the aforementioned optimization exploration. Performance, again, is measured relative to the performance of the baseline implementation. The x-axis shows the different configurations of optimizations that were evaluated in order to extract more performance. The first set of attempted optimizations cyclically partition the buffer that should be the shift register. The results for this are prefixed on the x-axis with the word partition. The partition factors are shown underneath the figure. Increasing the partition factor increases the number of banked memories and will add additional ports and could increase memory bandwidth. From the figure, though, it is clear that this attempted optimization further degraded performance. Looking at the kernel log shows that more resources were used while also increasing pipeline latency and decreasing clock speeds. The next set of optimizations evaluated was sizing the shift register buffer such that a shift register could actually be inferred by the hardware compiler. The sizing factors are shown underneath the graph. The results for these configurations are prefixed on the x-axis with the letters SR. The results labeled SR-turn attempt combining the shift register optimizations with using ternary statements in order to help the compiler reason about the computation, but we find empirically that the compiler is already able to do this without additional help from the user. Thus, the following discussion refers to both the SR and SR-turn results. From these results, we observe a performance boost over the baseline for each different shift register sizing, with the best improvement being a 3x speedup over the baseline when the shift register is 512 elements wide. Additionally, the compiler logs show that this kernel is now able to be pipelined with an iteration launching every other clock cycle. Although the performance benefit is not as pronounced as the results found in Zuhuri et al.'s work, this result reinforces the fact that FPGA constructs that are known to aid performance are theoretically portable. However, porting that construct across different FPGA vendors requires more than the minimal porting effort, making performance portability more difficult. To conclude, this work presents our efforts toward evaluating the portability and performance of HLS kernels originally designed for an Intel FPGA and porting them to a Xilinx FPGA. To perform this evaluation, we used a subset of applications from the Rodinia benchmarking suite and their corresponding Intel OpenCL FPGA implementations. We ported baseline single work item versions of those kernels, as well as the most performant versions of those kernels to a Xilinx FPGA. The minimum amount of modification to port these kernels varies. For some optimizations, there is a one-to-one mapping. For others, the process is more involved. Achieving competitive performance from these kernels is also non-trivial. While portability between vendors is generally poor, we show that FPGA constructs can perform well regardless of the vendor specification, though they might require additional modification from the user. Since this is our initial evaluation of portability and performance, there are many avenues for future work. A short-term goal is to port more kernels from the Rodinia suite to Xilinx OpenCLC in order to find more optimizations to explore and port. Another short-term goal is to directly use C or C++ when porting new applications. Xilinx provides HLS libraries and a wider range of control when using C or C++ for kernels. Thus, there may be Xilinx-specific optimizations that we could explore in order to extract even more performance. Our long-term goal is to take the lessons learned from our empirical evaluation and to automatically generate optimized Xilinx HLS kernels. With that, I conclude our presentation. Thanks for your attention. I look forward to hearing from you.